In the previous chapters, we have talked about the process and the thread. So in this chapter, we are going to discuss synchronization, basically how processes or threads communicate with each other through the synchronization manner. Although this chapter is called the process synchronization, but the technique can be applied to both process synchronization and the thread synchronization. Particularly in this chapter, first we will talk about the background of synchronization. So why we need to use synchronization. Then we will discuss the critical section problem. And next, we will talk about the hardware that designed for synchronization, and also based on those hardware, how the operating system provide different mechanisms to support synchronization, basically mutex locks and semaphores. At last, in Linux C programming, so with the help of a pthreads library, how can we achieve a synchronization there as a case study? Nowadays, due to the development of a computer technology, so we may have multiple CPUs in the computer system and multiple cores in each CPU, right? So therefore, the processes can be executed concurrently or even in parallel. So during the process execution, the interruption could be happened at any time, which results that so only part of the process get executed, and also multiple processes may concurrently access to the shared data. So during this procedure, when one process wants to access the shared data, the interruption happened. Then another process who wants to access the same data has been put onto the CPU, then update the data. So in this situation, the data inconsistency problem may be happened. So just like the cache coherency problem we have discussed in the previous chapter. So definitely we need to avoid this problem happened. Then we need to maintain the data consistency that requires mechanism to ensure execution of cooperating processes in order. So which means that those processes who share the same data must be executed cooperatively. So in order to avoid the data inconsistency problem. For better understand this data inconsistency problem, we will use the old problem which we has discussed in the previous chapter called consumer producer problem for illustration. So you may still remember that when we talk about the consumer producer problem last time, so we use the two pointers which are in pointer and out pointer to point to the next available atom slot and the next available new atom, respectively. Through comparing with in and out pointers, we decide that so whether the buffer is full or not. However, this strategy is not efficient enough because the buffer cannot be fully utilized. The reason is because we must leave an empty slot for in pointer. Otherwise, if the buffer has been fully occupied, so there's nowhere the in pointer can be pointed to, as we already mentioned. However, this time we will use another mechanism to allow the consumer producer problem can fill all buffers. So instead of using the in and out pointer to track the buffer, so we will use another variable called counter to track the number of full buffers. So suppose the size of a buffer is equal to n. If counter is equal to n as well, so which means the buffer is full. On the other hand, if the counter is equal to 0, which means the buffer is empty. This slide shows you the redesigned solution for producer-consumer problem. So we still use in and out pointers to point to the next available slot and atom. However, we will use the counter to directly track the buffer. On the top half of this slide shows you the producer process. So inside the while loop, we have another while loop to check whether the buffer is full or not. So we directly use counter to compare with buffer. If they are equal, which means the buffer is full, and the process will be stuck at this while loop. As long as the empty slot is available, the process will be out of the while loop. Then put the new item on the buffer slot, which is pointed by in pointer. Then increase the value of pointer in by 1, then round up the value of pointer in by buffer size. So remember, we are still using the circular array here. At last, increase the value of counter by 1, since a new item has been put onto the buffer. Then the whole process will be done again. After the counter gets updated, if the counter is equal to buffer size, the producer process will be blocked again. On the other hand, so in the consumer process, the similar procedure will be illustrated on the lower half of the slide. So within the while loop, we use another while loop to check whether the buffer is empty or not. If the answer is yes, the consumer process will be blocked in the while loop. If the answer is no, the new item, which is pointed by the out pointer, will be moved out from the buffer. Then increase the pointer out by 1 and round it up with a buffer size. So finally, decrease the value of counter by 1. Based on the description of a previous slide, the solution for consumer and the producer problem looks fine in the source code level. Then let's see it even closer at the assembly language level to see if anything wrong is there. So when we see the counter increasing instruction at the assembly language level, it includes 3 assembly language instructions. First, the value of counter will be stored into a register. Then increase the value of register by 1. At last, put the increased value of register into counter. Similarly, for counter decreasing instruction, we also have 3 assembly language instructions. We've stored the value of counter into a register, decrease the register by 1, then put the updated value of register into the counter. So for nowadays, the computer system have multiple CPUs and multiple cores in each CPU. So even with the single core CPU, we can still achieve concurrency to allow multiple processes run in interleaving manner. So for this producer-consumer problem, we suppose that there are 5 items already on the buffer, which means the counter size is equal to 5 now. Then we suppose the producer has been put onto the CPU first, then increase the counter. For instruction S0, put the value of counter into register 1, then register 1 is equal to 5. Then S1, increase the register 1 by 1. Then register 1 is equal to 6 now. Then the interruption has been happened. The consumer process has been put onto the CPU. Then decrease the counter. For S2, put the value of counter into register 2. Since the counter has not been updated by producer yet, the value of counter is still 5 now. Therefore, 5 will be stored into register 2. Then S3, decrease the register 2 by 1. Then register 2 is equal to 4. Then the interruption happened again. Producer has been put back. Then put the value of register 1 into counter. Then counter is equal to 6 now. Then the interruption is happened again. Consumer is back. Then counter has been updated by register 2, which value is equal to 4 now. At this moment, you may already see the problem. If we switch the order of S2, S4, and S5, the value of counter will be equal to 6. Therefore, you can see that, so when we allow the processes execute in interleaving manner, the value of counter is depending on the order of assembly language instructions. So definitely it is incorrect. For this phenomenon, we call it race condition. So we need to come up with some mechanisms to address this race condition problem. And those mechanisms are referred as synchronization mechanisms.